going to be kind of open. Okay, so let me start now. And please feel free to stop me and ask questions. Okay, so there are lots of parts for this talk. The first part 1 is completely just introduction, motivation for what I'm going to show in part 2. Part 2 there's going to be math, and then part 3 is just some problems, open problems. Okay, so let me start. I know a lot of people will have trouble understanding what I'm saying because I try to swallow some words, but I hope to slow down. So I'm going to give a biased introduction to a couple of fundamental information theory problems. So let's start. Wait. It's not. Oh. Okay, so Professor Uhama in the morning gave a very beautiful introduction to a much more general framework of sources, stationary sources, or even non-ergodic sources, a lot of it. So in this whole talk, I'm going to make things as simple as possible. I'm not trying to go into very general settings. So this would be the mathematics of digital communication as Shannon proposed in 48, where he said that if a sender X wants to communicate to receiver Y over a noisy channel, I'm going to use the math frac characters to denote channels. Is Q of Y given X. So it means this channel behaves like a memoryless channel. So it's what Professor Uhama said, discrete memoryless version. So you have some encoder who wants to transmit to this receiver. So the famous result of Shannon is that the maximum rate you can reliably transmit is the maximum over mutual information IXY. And there's also a max-min version of it, which means minimum over alt Q of Y. That's the version you saw in the morning's talk. Okay. So this is the point-to-point setting, and this has been well studied. Well, people have studied generalizations of this and so on. But one generalization that I'm interested in is the following. What if there are more than one sender and receiver? Can we obtain a similar capacity region? This has been studied for many, many years. And the answer is mostly no. That means we don't know the capacity regions, which is either a good news or a bad news. The good news is that you have lots of open problems. The bad news is that this has been open for some time, so it may be hard to do it, right? Okay. And there is one notable exception, which is a multiple access channel. So, and there are many advocates in this community. Some people say that why would one expect such a region? Why should there be such a region? Or why should one expect a single letter characterization, if you know what I'm saying? Or there are a few other schools of thought, but I'm going to argue that at least for some problems, we need to first resolve a particular question before we want to get into the philosophy of existence of certain types of distribution, or certain types of characterizations around. Okay, that's the part of my talk. So one of the fundamental open problems is the broadcast channel. So here I have, and I'm only looking at two receivers. That means I have a single sender, I have two receivers, and I have two messages, M1, M2, that go through a shared but noisy channel. So the receiver Y hears some noisy version of X, receiver Z hears some other noisy version of X, and based on the noisy version that the receiver 1 hears, they have decoded to M1 hat, and based on the noisy version the receiver 2 hears, he or she has decoded M2 hat. And the goal is to compute the capacity region, and this is not known. So this has been open for quite some time, maybe around 42 years. Okay, the other setting is interference channel. So what is this channel? This is two point-to-point communication. So I'm just talking to somebody here, and there's another parallel communication going on, except that since we're using the same medium, they're going to interfere. So whatever the receiver 1 hears, and it depends on both the transmitted symbols, and whatever receiver 2 hears depends on both the transmitted symbols. And again, the goal is to compute the capacity of achievable rates. And in my mind, these are two most basic problems, because if you think of things like relay channel or two-way channel, they combine aspects of these two channels. And these two channels are kind of, I don't think you can compare these two, because this is like removing the the transmitter cooperation in the broadcast channel. So if I remove cooperation, is not clear where it makes this problem easier or harder. Okay, so that's kind of the setting. And there's another reason why these two are different. That's the first motivation. So for these two regions, for these two problems, there are regions, or achievable regions, one for each, whose optimality or suboptimality has not been established for over 30 years. That means there are proposed regions for these two problems, which I mentioned explicitly, for which we don't know whether that is the answer or not the answer. Okay. So until we know for sure that that's not the answer, if we show that that's not the answer, okay, then we are back to square one. But that could be the answer because we don't know of any example where you can beat those regions. And for both these regions, there is a way to test the optimality or suboptimality. That means it's not only that they are optimal, suboptimal, but actually we can test it in some sense. I'll explain to you in a minute what I mean by test the optimality, suboptimality. And this is true in lots of settings, and sometimes a useful tool. The bad thing is the testing procedure requires infinite computational resources. That means you need to wait for infinite time. But however, if it's suboptimal, the procedure will terminate in finite time. Okay, so and this can be used to get some insight into whether it's optimal or not. So it's suboptimal, and if you're lucky, you can get a contradiction very quickly. But if it's optimal, you essentially have to run it for infinite time. Okay, so this is actually a good way of testing suboptimality, and we have sometimes employed it to get counterexamples. So what is the procedure? Okay, suppose your advisor gives you a region. Okay, he cooks up on some big messy region, which has a property that for any channel Q, it yields a computable region A of Q. So this is the region it gives for a particular channel Q. And as n tends to infinity, the normalized region goes to capacity. Normally, these are very, very easy to show using phenotype inequalities. That certain regions go to capacity. It is really the difficulty in getting a single letter characterization or a single computable expression. If somebody gives you such a region, and such regions are known for a lot of settings. Okay, in fact, most of the settings. So it's enough to test whether, if I go from 1 to 2, whether this inequality holds for every channel, or if this is true for every channel, then it's optimal, or if it's suboptimal, there's at least one channel for which this inequality is strictly tight. Okay, so what would you do? What I would do is I would take a computer, write up this region. I would compare the one letter with the two letter. I call this the two letter, and I would see if this matches. Okay. If it doesn't match, immediately I have a counterexample that the proposal is not capacity. And if it matches, then I need to see whether it's a chance occurrence or whether there's something more going on. Okay, that's a kind of testing procedure. Okay, but gives you a very nice way. That means I'm not going to devise anything new. I'm just going to do the same region, except I'm going to compute the same region for a different channel. Okay, I'm not asking anybody to come up with a new achievable strategy or nothing. I'm just within the same achievable strategy you can work and test it whether it's optimal or not. Okay. So this is what I'm saying, that for broadcast and interference, I think the only two examples for which we know this, and for two receivers, we have some regions for which suboptimality or optimality has not been shown. For almost all other examples, we have counterexamples to the optimality, suboptimality of them. Okay, so this is only these two problems are special in my mind. Okay, so what is for the broadcast channel? So I'm going to spend a lot of time on the broadcast channel, and a similar story is true for interference channel, but I'm not going to spend as much time on it. Okay, the first region is by Martin. This was in 79. She said that the set of rate pairs R1, R2 satisfying these three constraints for any UVW, such that UVW to X to YZ is Markov is achievable. Okay, that's her theorem. And so if you look at this, in fact, most people who look at this stop here, because it's extremely difficult to compute this union. because you have UVW, you don't know sizes of UVW. It is just an achievable strategy. Okay, and this seems daunting. And in fact, so I spoke to Martin last year when she was in the conference. The only reason why she proposed this region is because she thought it was natural, and she felt it was an interesting generalization of her proof for deterministic broadcast channels. She didn't have any other motivation in mind. She didn't know how good it is. She thought that she had a proof for deterministic broadcast channels. That means both channels are deterministic, and she wrote what would be a natural extension of that strategy. Okay, and this is the region she got. And at that point, there was no reason to believe that maybe optimal or its optimality was worth investigating. In fact, it was very hard because there was no cardinality bounds in UVW. So even if you want to evaluate this, it becomes very, very messy. Okay. So for any UVW, this gives you an achievable region. So it is union over all possible things, and this seems very daunting. Okay, that is so. So even though I said in the previous slide that yes, there are regions for which you can test the optimality. So optimality, when you look at this region, most people will give up, right? Because this is very, very hard to do on first sight. Okay. Now this is something that happened. So when I came here, when I joined this place about 6.5 years ago, I had lots of free time, and that's usually it's one of my grandfather says. So I had lots of time. And I said, okay, let me try to play with this region. Let me see what I can say about this region. Okay. Maybe I had too much time. Okay. So we wanted to evaluate Martin's region. And so the first example, I like playing with small examples. So the first example I had in mind was this example. These are two Z channels. X2Y is a Z channel, or this is an S channel and this is a Z channel. And why did I choose this? Because they are actually they are skew symmetrical. It means X to Y has the same capacity, point-to-point capacity X to Z, but they're kind of orthogonal. So these are channels for which there's no degradation. Each receiver is as good as the other receiver. You cannot differentiate between them. So, and for some kind of degradation, if one receiver is better, then we know what to do. So this is the kind of channel for which we don't know what to do. Until today, this capacity is not known. Okay? But my interest was to evaluate Martin's region for this channel and see if the 2-letter matches the 1-letter. And it took me about 2 years to evaluate this, which I'll tell you some of the techniques that were developed in the whole process. But it was an interesting. Okay, so quickly. So the first observation was that for this channel, 0 is completely noisy because if you transmit 0, it gets flipped with probability half. And for this channel, 1 is completely noisy. Okay. So one natural instinct would be that, okay, maybe some kind of time division is optimal. And so based on the intuition, I learned organized ITA, and I use ITA as a platform to put my intuitive reasonings out. Okay? It's like a place where not finished results, but some intuition out. So I put this conjecture out there that I believe that for this channel, for every UV to X to YZ, this inequality holds. Okay, so, and if this is true, then I could evaluate Martin. Okay, then luckily somebody in the audience paid attention. It was Venkat, and he asked the student Amin Gohari at that time. They caught the attention, and what they did is they developed the perturbation approach to try to attack the conjecture. And what they could show was that you can restrict attention to binary U and V. Why is it in blue? Because my second part of the talk, I'm going to show you what this approach is. Okay, that's what. So the second part is when I'm going to do the math, I'm going to show you how this approach works. It's a very beautiful argument. Okay, because it's not traditional. Okay. And further, they showed that okay, you can use the same ideas so that you can restrict U to be less than X and V to be less than X. Okay, I'm going to mention this in part 2. So this, just an attempt at showing this made them interested, and they developed this approach. But yet they couldn't prove the conjecture because but now they could kind of verify numerically that it holds for all randomly chosen things. And they they told me about it. I read their paper, and when somebody else read the paper, you have some other idea. So we extended their approach and showed the conjecture. Okay, so we kind of did something, but I'm not going to talk about this. And then once we showed this, that it was true for this channel, then we realized that the proof doesn't require that particular channel structure, or we can get around the used channel structure, and then we showed that it's also any binary channel. Okay, so even though I'm going to show a vanilla perturbation approach, there are much more fancier, and there are fancier versions of this already existing. Okay, in these two papers there are much more fancy versions. Okay, so what is perturbation approach? It's a technique to reduce the search space. Okay, it's also boundary cardinalities and much more of extremal auxiliaries. I'm going to define what extremal auxiliaries are. So what are extremal auxiliaries? So achievable regions or outer bounds in information theory are usually written as a union of regions. You just like Modman, the union over U, V, W, each corresponding to a distribution over random variables, okay, including auxiliary variables. So this gives you some region, okay. Some union gives you a region which might look like. No, I'm not going to do, and this is going to be 1 sec. So it might look like this, okay. So this may be unions of lots of regions of this type, but those distributions that give you boundary points, that's what I call extremal distributions. Okay? We don't know what they are, but this is operational definition. If you look at those auxiliary distributions that give you the boundary points of the union of overall distribution, those are extremal. Or in some sense, if God tells you that, okay, these are extremal distributions, then I just need a union over these distributions, right? I don't need takeover. So that's the kind of things I'm talking about. Can I restrict my search space to something much smaller? When you want to compute in a computer, that's very useful, right? If I don't need to search the entire space, but I'm telling you I need to search only this space, that's very useful. So that's kind of search what we started taking. So what are the uses of character? So that's what I said. If I characterize the extremal distribution, or if I say that, oh, it's a subset of a smaller set, then this makes computation much easier. So you can verify this quite easily. But also we could utilize properties of these to maybe show that, oh, you have a class channel, maybe in this case the inner and outer bounds might match. And this is exactly what is used in the MIMO Gaussian broadcast channel by Weingarten, Steinberg, and Shamai. This won the best paper award. So this was like a big paper, but the whole idea is to show that certain bounds match. To show that certain bounds match, they had to compute extremal auxiliaries, they had to show various kinds of arguments and so on. But this is too much to cover, or there's a way that gets around this now. So I'm going to cover a much simpler case, BSC and BEC. I know that Rudy likes binary symmetric channels, so I'm going to use just BSC and BEC. And this also involves representation in concave order. So these are blue things I'm going to show. Okay, this I'm not going to show. So this is in the part 2. So that's what I'm going to do. So that's the end of part 1. So part 1 says that, okay, there are regions in terms of auxiliaries, but I'm going to focus myself on extremal things, the things that give you the boundary. That's enough for me to look at. Oh, good question. Can somebody else answer? Why is it enough for 1 to 2? Oh, maybe I should clarify. It's 1 to 2 for every Q, right? For every channel. If I show 1 to 2 for every channel, that's enough. Why? Because 1 to 2 is 2 to 4, 2 to, like 2 to 4 is 2 of 2, right? 2 to 4. Yes, for every channel, we take an arbitrary channel, show that that's equal to 2. So then any powers of 2 is just the same thing.
Then I see if you have no cardinality bounds.
Yes, no cardinality bounds in any Q.
But it's not just here that cardinality.
Cardinality bounds. No, I'm saying you take any discrete memorial channel, an arbitrary, generic channel, you show that 1 to 2 matches. So using some technique, that's enough, right? Because you consider the class of, whatever you do, it's a finite alphabet, right? Maybe, is it clear? No. Like, it's not enough to show for binary channels, right? It's not enough to show, if I show this for binary input channel, that's not enough, right? I need to show for any generic finite alphabet channels, if I show this, that's enough. Right? I take an generic channel of some cardinality. Is it clear? But that's enough, because we know that the limit there's a limit. Okay, and we know it's subadditive, so it's, I mean, any subsequence will be enough. Okay, that's why powers of 2 is enough. I mean, that's easy, because you have anything else you can do powers of 2 plus something. I mean, that's a very simple. But that's a good question to ask. But this is a very simple. The good thing is that this is a very good way to test, right? You just take randomly channels, and if once and most cases where you can get counter examples very easily, and you immediately know that that's not the right region to look at. At least for small example, and if you see that they are matching, there must be some reason. Okay, I'll come back. And this will come apparent later. This is quite.
Because it could be that from 1 to 2 it's the same, then from 2 to 3 it goes up, from 3 to 4 it goes up. So then, no.
Like, there's a subadditivity. That's very simple to show. Okay, there is subadditivity for the rates. I mean, you can just block separate. This is. I think this was observed even like 70s. I think Witzenhausen uses all the time. I mean, so when he wants to show for n, he just shows 1 to 2, and that's kind of the simple. Okay, now I'm going to get into math. Okay, so we have. So hopefully this is just intuition. So now I'm going to get into math. I'm going to use visual present at some point, and so let's go slowly. So what is the old-time tools for restricting cardinality bounds? It is essentially Carat-Theodory's theorem. Okay, it's like 30, 40 years ago. People use this theorem all the time to restrict bounds and auxiliaries. And I want to go through this because for various reasons, I think it's a good. Very rarely is this taught in many classes. A, B, I've reviewed many papers where they use this result wrongly, and C, I don't think people know why this is true. So that's why it's a good exercise to go through it. And here's an example. Suppose you have multiple access channel. The capacity region is a set of all rate pairs satisfying R1 less than this, R2 less than this, R1 plus R2 less than I, X1, X2, Y given Q for some PMF with Q less than with 2. Okay. Now here, this is what I want to concentrate on. Why should we only take 2? I'm going to show you why. Okay, so if you think that people know this all the time, it's very simple. Okay, for interference channel, you still have a similar Q. Okay, and the Q was like 6 or 7, but then, I mean, I was explaining this in the class, and Babak showed that you can take 5. That's enough. Okay, so people haven't optimized this, and why am I interested in optimizing? Because I want to simulate. That's the only reason. I want to get it down as low as possible. So, and this is just vanilla Carat-Theodory. Okay, what does vanilla Carat-Theodory say? So it says that if a point in a d-dimensional Euclidean space lies in the convex hull of points from some set E, which is a subset of Rd, then that point can be written as a convex combination of at most d plus 1 points. So if it's in Rd, if a point in Rd is a convex combination of some points in the set, then I can take convex combination at most d plus 1 points from the same set. Okay, so I'm going to show the proof of this. So I'm going to be slower because otherwise I will. So what is a convex hull? Convex hull is a set of all finite convex combinations of points in E. That's the smallest convex set containing E. So it's a set of all finite convex combinations. Okay. Now suppose my point X is written as the following convex combination. That means it's Pi EI. EI is a point in E, so this is a point in Rd. This is a probability weight. It's a convex combination. And I assume that K is bigger than D plus 2. Why? Because if it's D plus 1, there's nothing to show. And I'm assuming that all the PIs are positive. Why are all the PIs positive? Why can I assume that PIs are positive? Why are they not negative? Because if it's 0, then I don't need to use the PI, right? This kind of minimal representation. If it's 0, I don't need to use the PI. And summation is 1. So I'm assuming that all are positive. Okay, then I claim that in this code, I can find weights Wi, which has these two properties. Wi EI is 0, that means I have a linear combination which is 0, and Wi is a 0. Why is this true? Okay, so let's see if somebody's aware. This is from students. This should be easy, obvious. Is it clear? No. First one is linear dependence. Great. Why this? Yes, so d plus 1 is fine. You get this for d plus 1. But I'm also saying that I can sum of the weights is 0, right? I can assume that sum of the weights are 0. That's d plus 2. You know why? Because suppose I take one linear combination using 1 to d plus 1, at least one of them is non-zero, I remove that. I take another linear. Okay, maybe I should go over this slowly. I mean, but once you know this, you're done. Okay, so let me just go over this slowly. So let's see what Professor wrote. So maybe I'll just write this here. It's very simple. So, but it's a, or should this can be an exercise for tomorrow? Yeah, that's better. So this is an exercise for tomorrow. You can try why this is true. This is true. Okay. So this is a. Okay. Okay, now what do? I just take pi minus epsilon times wi. I just subtract from this a weighted version of this expression because this is 0. This is still x, but now I can choose epsilon large enough to make one of these quotients to be 0, right? Because at least one of them is non-zero, so I can make one of them 0 by choosing epsilon large enough. So what have I done? I've reduced support by 1. So the moment I have more than d plus 2, I can reduce by 1. And note that I'm using the same set of points. I'm just using a subset of the points, reducing support by 1. Clear? So the reason why I needed this to be 0 is so that this remains a probability vector. The sum becomes 1. And if epsilon is small enough, then all of these are non-negative because pi was strictly positive. So when epsilon is 0, they still remain positive. So I increase epsilon till the first point, one of them becomes hit 0. That's the where I stop, and I drop it. Okay, that's the idea. So that's Kara-Theodry. Okay. There's another reason why I want you to look at this proof of Kara-Theodry, because Amin's perturbation argument, which I'm going to show, has a very similar flavor, though it's very much more powerful. There's a very similar flavor of going in some direction, which doesn't change the function, then till I can drop the support. Okay, the same kind of idea. So I'm going to show that when something happens. Okay, now I'm going to go to another fact. People use it, but so this is Bund's extension. It says that, okay, now if a point lies in the convex hull of points of E is in RD, and E is at most D connected. That means E has connected components, but at most D of them. Okay, then X can be written as a convex combination of at most D points from E. So that means I'm reducing from D plus 1 to D. My only condition that my set must be D connected. Okay, this I will use the visual present to show why. It was a very nice, very cute idea. At least for 3 it's enough, and for 4 I don't know whether my drawing skills are good enough to show it. Oh, D connected means, okay, this is, yes, I will explain that. Okay, so what is D connected? Okay, this set is connected because I can draw a path from any 2 points, and the full path lies in the set. That's connected. This is 2 connected because I have 2 separate connected components. This is 3 connected, right? I'm not saying the set, the original set is D connected. Then you're taking the convex hull of that. Okay, so if my original convex combination comes from a D connected set, then I only need D points. Clear? Okay, so let's prove this. So what is Bund's theorem say? That means if my convex combination is from a D connected set, then I only need D points. Okay, let's prove this for D equal to 2. D equal to 2 is nice because I'm on a plane and I have a paper as a plane, so it's very easy to draw. So suppose not. Okay, suppose there is a point. Okay, let me try. Suppose there's a point here. Okay, this is the point. Okay, this is not visible. Okay, this is the point I want to express. This is by Kara-Theodry clearly. I need only 3 points, at most 3 points, because I'm 2. D plus 1 is 3. So let me just say that okay, there's 3, but there is no 2 points that give me the convex combination. So this green spot is the convex hull of these 3 points, right? It's a triangle, right? Now how do I show that this is not possible if my original set E is 2 connected. Okay, how do I show this? The argument is, okay, let me try to draw the argument. It's actually quite simple. So what do? I look at the line joining this point and the green point, extend this. Okay. Can any point on this line be in set E? Can any point in this line be in set E? I claim no. Why? Because if any point in this line segment lies in E, then I could take the convex combination of these 2 points. Right? And this would be in the middle of it because it's the line segment. So, right? Similarly, look at this extension. No point in this line can lie in E. No point in this, I mean, this is just extension of this is just extension of this, and this is just extension of this. This cannot lie in E. Oh, E is supposed to be at most 2 connected. E is at most 2 connected. Okay? At most 2 connected. And I'm assuming that there's a point we can only be written as a convex combination of 3 points, not 2 points. So these 3 cannot be in E, but this belongs to E, this belongs to E, right? Because this belongs to E. I've just separated the space into three distinct parts, each which contains E. Like this region contains a point in E, this region contains an E, this region contains an E, but they are separated by these planes that don't contain E. That contradicts the 2 connectedness. Because there has to be at least 3 connected, because I cannot go from any point to the other point without crossing a boundary. Is that clear or no? That's too. That's all that. I mean, is this clear or no? I mean, you guys have taken my class, so that doesn't apply to you. Oh, because if this point was an E, then I could take the convex combination of these 2 points and I would get this. So then that could be expressed as a convex combination of 2 points. So I'm assuming that there's a point that cannot be expressed as 2 points. Okay, for 3, what would you do? For higher dimension, what do you do? Just draw the tetrahedron with these points, extend it, look at the faces of that separates the face. That's it, that's the whole proof, okay? So we use the fact that it's connected, so to get this, so that's Bund's theorem, okay? And this was done in 1935 or something. It's a very old theorem. And I don't think there's an English version, so this proof I read it from some like a 1-2 page math paper sometime. So it's very nice. I like this idea because it's very clean. Okay, anyway, so let's go back. Okay, now how do I complete the Q equal to 2? Okay, so the first thing you want to observe is that every boundary point corresponds to some auxiliary distribution. Now I claim that it suffices to find some other set of distributions Q prime, x1 given Q prime, x2 given Q prime, with Q prime at most 2, such that these 2 conditions hold, or these 2 conditions hold. Because the MAC, you have 3 constraints, but only 2 can be activated at one point, and if you have the two active constraints, the third is automatically satisfied. So that's because when you look at the MAC, it cannot be that these 2 are satisfied. I mean, if these 2 are tight, then this condition will hold, or if these 2 are tight, then this condition will automatically be satisfied. So if I fix these 2, because this plus this is bigger than this, that's very easy to see. So you can think why. If you don't know, you can think why. So you just need to preserve these 2. Okay. This why is questions thing. So even if I don't put in Piazza, this is just there's something to think about. Okay. Why is it enough that 2 of them? The same thing if I do for Han Kobayashi, that's what Babak showed, that you don't need 5. You don't need, that's a lot more, but you don't need 5. That's much more. Okay, so how do I complete the proof? So look at the mapping from the set of all product distributions to this pair of points in R2. So if my first coordinate is, say, okay, suppose the boundary point comes from these 2, I'm fixing these 2, then look at the mapping to this point in R2. Okay, that is my set E. And I claim that E is connected. Why? Because this space is connected and I have a continuous mapping. So if I connected space and I have a continuous mapping, the range is connected. So E is connected. And this condition Q is just convex combination. So this is the convex combination of points in E. Therefore, by Bund's theorem, you only need to take 2 points in E. So that's exact. So you need Bund's theorem to ensure that you can take 2 points in E. That's the whole proof. Okay. So, but Yeah, so these are the details of the MAC proof. So that's the prehistoric tools. Okay, so let's do. Okay, now so now let's look at Amin's perturbation-based argument, and let's see what it can do. So the question really becomes: suppose you want to maximize over all distributions UV condition X this expression IUY plus IVZ minus IUV. Why does this come about? Because you can either from the information inequality or from Martin's region, this is an expression that comes about quite frequently. And what Amin showed with Venkat is that UV is less than or equal to X. Okay, the first question should be that why doesn't Carré theory suffice, or why doesn't the usual technique suffice? It's because if you think over it, if you want to bound a cardinality of U, this is problematic. You can do it, but in terms of size of V. You can bound the cardinality of U in terms of size of V, but similarly when you try to bound the cardinality of V, it's in terms of U. So they become coupled and you have no control. That's really the issue with this. And so what he's going to do is something different. Okay, let me do the whole thing. I have the whole thing on the slides, but I don't want to do it on slides, because slides I will just run through very quickly. Okay, but it's a very nice argument that I think it's better to do it on the paper. So and this will slow me down too. So please feel free to ask questions if it's not clear. Okay. Let me change this. Okay, let's see what is the argument. So I want to maximize. I want to maximize over. Is this too small, or can you see it in the back? P U V given X. So the distribution X is fixed. The channel is fixed. IUY plus IVZ minus IUV. Okay, this is going to be a longish proof. Okay, I mean, in the sense it's going to take some time. So, okay, so I can write this as UV to X to YZ, and this is my channel, and I'm maximizing overall UV that's it behind X. This expression. Is that clear? That's okay. Okay. And now my claim is I can set size U to be at most X or size of V to be at most X. Okay, that's what I want to show. But let's start with this. So I claim this is equal to, let me expand this into entropies. H of U cancels here. H of Y plus H of Z plus H of UV minus H of UY minus H of VZ. Okay, why? Because this is very simple. Mutual weight is the sum of the entropies minus joint entropy. So expand some of the entropies. H of U cancels out, H of V cancels out, H of Y remains, H of Z remains, H of UV comes with a positive sign, and that's it. I mean, it's just straightforward manipulation. Clear? I'm expanding IXY is H of X plus H of Y minus H of XY. That's what I'm doing. Okay. Does this change? This doesn't depend on PUV given X. It only depends on X, right? Because X is fixed and channel is fixed. So this is fixed. This is fixed. So this is really same as asking maximize over PUV given X HUV minus HUY minus HVC. So this is the same question. I'm going to ask. I'm given it to X. I want to maximize this expression. Just removing this. That's what I want to do. Rudy is still staring. Is that okay? Okay. Is this clear? What I'm trying to do? Okay. So now, what is the trick? So let's say that P star UV given X is a maximizer. Okay, this is a maximizer. Then I'm going to take P epsilon. I'm going to perturb this in the following way. Is P star UV given X times 1 plus epsilon L of U. So this is my perturbation. I'm going to perturb it. I'm going to get a new distribution in this following way. Okay, what is the condition for that? This is a new. What is the condition for this to be a distribution? What is the condition for this? What is the condition for it to be a distribution? The elements must be non-negative and they add up to 1, right? Non-negative is easy because if I take any L, I can choose epsilon small enough to make it non-negative. Right? As long as epsilon is small enough, the things will become non-negative. To make it add up to 1, what do I need? I need that summation probabilities are 1 for every x. That means I want for every x summation p star u v given x, this summation over u and v, L of u must be equal to 0 for every x. I'm not assuming they are positive. If it is 0, p epsilon remains 0 because I'm multiplying it by something. Right? So that's okay. This is a multiplication. So if this is 0, this remains 0. With positive, I can do this. Right? Okay, that's a good question. So you need that this is 0 for every x. Okay? Because otherwise it's not a probability distribution. It's not a probability distribution anymore. So I want this to be 0 for every x. So what size of u? I claim that if u bigger than or equal to x plus 1, then there is a non-trivial L of u. Why? Again, same dimensions. You have linear equations, you have x of them, and if my number of variables L of u is more than x, then my null space is not empty, right? So I can find a non-zero vector in null space, right? There are exactly x equations. So that's my argument. So if u is bigger than x plus 1, then my null space is not empty, which means I can find a vector. So this is my perturbation direction. And what I will show in about 10 minutes is that all along this perturbation, the value doesn't change. And therefore I can move this perturbation along till I drop the size of u. Okay, I can choose epsilon large enough so that I make this one of them to be 0. Okay, that's exactly like Kara theory. So how do I show this? Okay, so let me define my S epsilon to be H epsilon. By epsilon I mean I'm using the P epsilon. H epsilon uv minus H epsilon uy minus H epsilon vz. That's my thing I want to maximize. And we know that P star is a maximizer, so we know that S of 0 is a maximum. So what can I say? D by D epsilon, S of epsilon at epsilon equals 0 is what? 0 because the maximum. And what is my second order condition? D square by D epsilon squared, S of epsilon at epsilon equals 0 must be less than or equal to 0. These are my two conditions for being optimal, correct? So I'm going to use these two conditions to show that they are a constant. So this is where I say that this is different from the Kara theory because this only works with the optimizer. It doesn't work for anything. Here I'm explicitly using the fact that I'm an optimizer to get the direction. Okay, how do I show this? Okay, let's do some calculus. It's not bad. Okay, let's do just, so you need to take the second derivative. I'm going to do second derivative first. So I won't take second derivative of this term. Other term will be similar. So let me start with this term. So let me write what is P epsilon Vz. What is P epsilon Vz? is equal to summation over all the other things. So u x y p epsilon uv given x times p of x, or this, right, times q, this is my channel yz given x. Now let me expand this. Ux and y, p star uv given x times p of x times q yz given x times 1 plus epsilon L of u. I'm just writing for p epsilon, I'm just substituting, nothing more. Now I get some more y, that's easy. So when I do without, when epsilon is 0, what do I get? I get p star vz, that's exactly what I get, plus summation plus epsilon times summation over ux p star uv given x p of x times L of u times q of z given x. Right, that's what I get, and somehow y I get just this. So there's a way to write this. Okay, let me write this because it may be hard for you, if it may be half fluent, maybe sleepy. Let me just write this. This is nothing but the conditional expectation of L given Vz, right? Because how do I get the conditional expectation? I sum over times P star Vz. Right? This is exactly what happens, because if I multiply by P, conditional expectation, I divide by P star Vz. So when I multiply by P star Vz, I get the joint distribution. That's exactly, I'm summing over U and X, and I'm averaging over L. That's what I get. So that's the expression. So it's P star Vz. This is a general expression. So P star Vz into 1 plus expected value of expected value. I mean 1 plus epsilon times L given Vz. So if I had Uy, I would get Uy here. If I had anything, I would get the same thing here. So this is what happens when you do P epsilon. Now what is entropy? H epsilon of Vz is what? Negative summation over V and Z P epsilon of Vz log P epsilon of Vz. Okay. So let's write d H epsilon of Vz by d epsilon. What is this? This is negative summation over V and Z. If you do this, you get, I mean, I'm taking log to natural base, so log of P epsilon of Vz d P epsilon of Vz by d epsilon. That's negative summation log P epsilon of Vz. Okay, let me see how many are awake. How do I go from here to here? Why is this true? Why can I drop the 1? Yes, because summation over probabilities are 1. So even when I perturb, it's still a probability. So the value doesn't change. That's why I can drop it. That's unfair. You took my class, so it's not quite fair. Okay. Anyway, so this is log. Okay, and this is linear. So what is this? This is negative summation over V and Z P star of Vz, expected value of L given Vz log P epsilon of Vz. Okay, now let's take the second derivative. What is second derivative? I have just epsilon here. So d squared, just bear with me because there'll be something nice happening. D epsilon squared. So this constant, P star of Vz, expected value of L given Vz by P epsilon of Vz, right, times dP epsilon of Vz by d epsilon, which is what? is negative summation over V and Z. So this again I know what it is. It's P. So it's P star of Vz, expected value of L given Vz, the whole squared divided by P epsilon of Vz. Okay. Now when I put epsilon equals 0, what do I get? P epsilon becomes P star. So d squared H epsilon of Vz by d epsilon squared becomes negative summation over Vz P star of Vz, because one of them cancels, and then you get expected value of L given Vz squared. Oh, this is negative expected value of L given Vz squared. Right? I mean, that's essentially what I'm doing. I'm computing the average of the squared values. Of course, this is non-negative, so this is negative. So you can see the entropy is concave. I mean, so this is all nice. Okay, so this is why entropy, the second derivative is negative and so on. So this is a nice calculation. Now, how am I going to use this? So this is a nice, but keep this. This can be useful later for many other things. Okay, once I do this, let's go back to this. We know that this is less than or equal to 0. Okay, let's plug this and see what I get. I'm going to use the second derivative calculation. So this implies, so let me use this. Let me see if I can, let me put this, okay. So d squared by d epsilon squared S of epsilon at epsilon equals 0. What is this? This is d squared by d epsilon squared H epsilon of uv minus H epsilon of uy minus H epsilon of vz at epsilon equals 0. But I just computed what that is. That is negative expected value of L given uv squared plus expected value of L given uy squared plus expected value of L given vz squared. Correct? That's because I just told you that that's what the second derivative computation is. And we know that this must be less than or equal to 0. Okay, here is what happens. What is L a function of? L is just a function. I took L to be just a function of u. Okay? So if I give u, then what is the expected value of L given u is just L. Because I know what u is, therefore this is just L. So this just becomes minus expected value of L square. I'm given u, therefore L square. This also I'm given u, so just L square. I'm conditioning, I'm giving you the entire thing. So it's L square plus expected value of L given Vz, the whole square must be negative. These two cancel out. I have the second moment of something to be less than or equal to 0. What is the random variable? What must be the random variable? Must be 0 with probability 1. Which means, this is kind of the magic, which means that expected value of L given Vz is 0 whenever, if you want to be precise, P star Vz is positive. Okay. Whenever the P star Vz is positive, then this must be 0. Okay, now let's plug back here. What is my P epsilon of Vz? Where was I? Shouldn't be here. Yes, P epsilon of Vz is P star Vz into 1. Where do I see this? 1 plus this. This is the thing I said it's 0. Therefore, as a consequence, this implies that P epsilon of Vz is exactly same as P star of Vz. Which means that H epsilon of Vz is H star, doesn't change. It doesn't depend on epsilon. So which means this implies that H epsilon of Vz doesn't change in epsilon. Okay, so that's good. So this is the problematic term. Okay, now let's go back to S of epsilon. So this is one of the magic that happens. The second magic is, so that it doesn't change its direction. Now let's second magic is the following. So let me go back. S epsilon is H epsilon of uv minus H epsilon of uy. Since it doesn't depend on epsilon, I'm just going to write HVZ. It doesn't depend on epsilon. So let me expand this. This we know is negative summation P star of uv into 1 plus expected value of L given uv is just L. So expected value of L of u log P star of uv into 1 plus expected value of L of u. That's my first term. Right? Because expected value is just the same thing. Plus summation P star of uy. Again, I'm given u, so conditional expression is same as the random variable. L of u log P star of uy times 1 plus expected value L of u. I missed an epsilon? Yes. And plus summation P star Vz log P star Vz. Okay, now second thing that happens is that the non-linear term, the log of product is log of sum, so this splits. And what does this become? This V cancels, like the V sums over, you get P star of u times 1 plus epsilon L of u times log 1 plus epsilon L of u. So I'm separating this out. So you don't have V. And look at this term, same thing. This with a minus sign, this with a plus sign. So I claim that this is exactly equal to negative summation P star of uv 1 plus epsilon L of u log P star of uv plus summation P star of uy 1 plus epsilon L of u log P star of uy plus summation P star of vz log P star of vz. That's my S of epsilon. What is this in epsilon? It's linear in epsilon. Correct? It's linear in epsilon. There's no, the log terms cancel because the log terms exactly cancel. The 1 plus log of 1 plus epsilon L of u, they cancel with the plus and minus signs. Okay? So this is the second thing that happens. The nonlinear terms cancel out exactly. Okay, so let me say a clever thing was choosing L only as a function of u. You could have chosen L as a function of u and v. But the moment you chose L as a function of u, things became much simpler. That's where his art form was. He just chose L as a function of u. You got this. You have a linear function. The first derivative is 0 at 0. So what is that function? It's a flat line, it's a constant line, right? We already know that d s epsilon by d epsilon at epsilon equals 0 is 0 by maximality. So even the linear term, that it must be 0, right? Because I get a linear term. So this implies S of epsilon must be equal to S of 0. So it doesn't change for any epsilon. I don't take epsilon small enough, right? I just expand it. So for any epsilon that's valid, this must be true. So this is why, okay, let me go back to, okay, I can upload this later if you want. It's all there in the slide. So everything is there in the slide. So there's nothing that, but I just want to go on the board so that you can follow the calculation easy. Okay, so let me go back to the PC. So this is you can go, as Chandra, I love you, x is bigger than x. And you have the first derivative, second derivative conditions. And you have the fact that, you expand p epsilon vz, you do the computation, you get this. second derivative squared. Oh, if you do it in continuous random variables, you get something like Fisher information, but this is a discrete analog. And we choose this, and you get d squared by d epsilon squared less than or equal to 0. So do the same calculation. So you have s epsilon is linear and epsilon first derivative equal to 0. So this must be 0. So again, choose epsilon large enough to reduce support of u by 1. So in this sense, the proof is very similar to Kara theory. You move in a direction which doesn't change the function, still you can reduce support by 1. Okay. At this point, you might think that, oh, this is very special. It only happens for this functions or whatever. Okay, so before I go there, so you can repeat until u less than x and v less than x. Now, but this argument, you can generalize it to prove the information inequalities, which I said before. And also, you can use it to restrict space by extremal distribution. So this is not like a very special argument for this particular function. As long as you can construct these L's cleverly, you can use it in a variety of situations. Okay, I'm also cheating. Okay, there are two things I'm cheating a bit. Perturbation arguments in information theory are very, very old. Okay, one of the first uses was to prove EPI, entropy per inequality. Okay, but again there, so, okay, in fact, the idea is almost similar, but there you know the direction to perturb. You're going in the straight line towards Gaussian. Okay, here you just show that there exists some L of u. Okay, and it's even more complicated here because here we don't know any direction, so there are much more fancier versions. But this will be the discrete analog of the proof of EPI in some sense. Okay. No, whenever you x plus 1, you have a L of u, right? Because you have only x constraints. Whenever you have one more variable, you have a non-zero vector. Whenever you have an L of u, I can make it reduced by 1. For Kara theory, I needed the sum to be 0 and the sum of the coefficients to be 0. I needed two constraints. I needed two additional linear constraints. That's why I needed another additional one. Okay. So this is why. So this is a.
We got a little bit lucky in the sense that the function you wanted to optimize, there's a straight line in the distribution space that goes from some optimum. Like, is it conceivable that some functions you're interested in, like maybe you have to follow a quadratic line or something more complicated?
Yeah, in the Gaussian case, you get a square root t line, right? I mean, you follow the power. You don't follow the straight line. You follow the power. I mean, in this case, so straight line.
So
LFU is not a straight line. LFU is just an arbitrary function.
Oh, but perturbing epsilon.
So you just find a direction, right? Where it just is. So LFU is not, but in Gaussian actually it's much. You know the direction. It's actually straight. It's like a power line. Okay, so that's the first part. So maybe it's a good time to take a break because, but not for coffee. I'm just saying that because it's a good time to ask questions. Okay. Is this clear? So this is a way to show that you can. So this is the first. I mean, Kara theory or something. Any point in the convex hull, I can write this as a combination of other points. Okay, small number of points. But here I'm critically using the fact that it's a maximizer. Why? Because I'm using the derivative conditions, right? Suppose 3, right? 130 to 3. No, the full. No, full talk. Oh, okay. Oh, okay. No, I'm not running the full talk, so I have to part 2, part 3. So but food's around, right? Okay. So we use the fact that we use this critically, right? So this is only true for the extremal distribution. So this is a kind of this is what I'm saying. So extremal distributions have some property that allow you to maybe restrict the space. So this is kind of the first instance of something like this happening. Okay, so before I go to this, maybe let's take the coffee break and then come back after 15 minutes. Any questions? You can ask me in the coffee break too. So if you given its
dimension. Use epsilon to reduce the cardinality.
well, I found a direction because we maximize it. Oh, I just take epsilon large enough. So
Yeah.
so you missed that point.
Yeah.
That's the same in karate theory too. So you have this,
Yeah.
and for any epsilon, as long as there's a valid perturbation, the function remains constant. It doesn't need to be small. Right? For any epsilon, it's true. Because why is it true for any epsilon?
So what's true for an epsilon?
Huh?
What is
Means
true?
I don't need epsilon to be arbitrarily small, right? It's not
Okay.
epsilon equals 0, right?
Okay.
Why? Because I just expanded it.
Yeah. Enough.
Okay.
Yeah.
So now I just epsilon. So when I start with epsilon equals 0, all terms are the same, right? I start increasing epsilon. What is my condition for this to a probability vector? All these terms are non-negative, and they sum up to 1. What is going to happen when epsilon becomes positive? You're going to hit the non-negative. One of them is going to be 0.
Okay.
Okay. At that point, stop. So you suddenly reduce the size of u, because if you look at the u, you reduce suddenly put that u to be 1.
And what kind of information equality?
Oh, the one I showed you, like showed with this. Oh, this is like. I showed that for any this one.
The one that was in the conjunction.
Forget this. Whenever x is binary, I can show this.
Okay.
It doesn't have to be channel. Whenever x is binary, I can show this. So it's a strong version.
And when x is not binary,
It's not true.
it's not true. You have
Yes. Yes. So it's just a math inequality which you can prove.
Excuse me, Professor. What did you say was old and you mentioned EPI?
Oh, because the perturbation technique is old.
Oh,
The EPI is proved using perturbation techniques. Are you aware of the proof?
EPI?
Yeah.
I know. Which proof uses perturbation?
Almost all the proofs use perturbation. There's no perturbation. There's no proof without perturbation. Oh, yes, there's no proof without perturbation.